Hello, my name is Mohammed Abuzar, and I have my colleague Shi Ding. We will be both presenting the paper, Bringing Cloud Native Storage to SAP IQ. First, I'd like to acknowledge all the following engineers who have worked on this project. Now, the topic of the paper is bringing cloud native storage to SAP IQ, but to put things into perspective, it's better to take a step back and understand how we brought SAP IQ to the cloud to begin with. So I'm going to give a quick introduction of what SAP IQ is. So SAP IQ is formerly known as Sybase IQ. It's a columnar RDBMS with many features supporting OLAP workloads. It has been built from the ground up to support these types of queries, and SAP IQ benefited from 3 decades of R&D work in this area. SAP IQ supports many features. Some of them, these are a subset of them that are listed on this slide. But I'd like to focus on 3 of these features which are relevant to our discussion here. The first feature I'd like to talk about is the prefetching engine in IQ. The prefetching engine in IQ has been specifically tuned and optimized for different column and index types. And the prefetching techniques used by the prefetching engine go far beyond sequential block-based prefetching. The second feature is the optimized load engine. Being an OLAP system, it's imperative that loading data into SAP IQ is as fast and efficient as possible. As a result, significant engineering work has been put into parallelizing SAP IQ's load engine so that we can speed up load operations by maximizing CPU and I/O bandwidth. The third feature that I'd like to focus on is elasticity of SAP IQ. So SAP IQ has a distributed compute model over shared storage. Compute nodes can be easily and independently added to the system without changing the underlying storage system or the way data are partitioned. So this mode of operation is called IQ multiplex. Now, let's talk about the storage requirements of SAP IQ. There are 2 main requirements that are needed from the storage system. The first one is that it has to be a shared storage system. And the second one, the system has to provide a strong consistency guaranteed. What this meant is that for the first release or the initial release of SAP IQ on the cloud, which is known as SAP HANA Cloud Data Lake, we had to use a block storage device on the cloud. An example of those that are available is Amazon EFS and NetApp Cloud Volume services. Now, these systems or these block storage devices on the cloud operate at a higher cost than other types of storage systems. So this brought the question is, now that we have SAP IQ running on the cloud, can we do better? Can we achieve better cost and better performance that we can achieve with these types of block storage devices? So we came up with this comparison table between different storage systems based on different criteria: consistency, latency, throughput, elasticity, reliability, and cost. And here we are comparing 3 different storage devices. First one is block storage, which is conventionally found on-premise installations. The second one is block storage on the cloud, which examples are EFS and NetApp, and object stores, which example of those are Amazon S3 and Azure Blob. it's quick to see from this comparison table that object stores offer higher throughput, higher elasticity, and reliability at a much better cost than the other types of storage systems. So it was important for us to explore the use of object stores in SAP and IQ, and that's what the topic of this paper is. So let's take a look at an overall architecture of IQ. At the top, we have a load and a query engine, which sits on top of a storage manager. And the storage manager manages the store on a shared block storage device. On the shared block storage device, we store files, which are a collection of blocks. So in order to utilize object stores, we asked ourselves, what should we store on object stores? And our first attempt, and we have built a prototype of based on this attempt, was to store complete IQ files on object stores. Now, IQ files are large objects. They are in the gigabytes to terabytes in size. And when we store these objects when we store these files on object stores, this means we cannot make updates to these files. So once a file is moved from a block storage device to an object store, access to the data in that file has to be in read-only mode. We cannot make updates. What this meant that if we needed to make updates to the files, that we need to move the file back to a block storage device in order to make updates to it. And this operation of moving the files back and forth between shared block storage device and object stores is time consuming and can saturate the network. There are also other issues that we have uncovered, is that many of the file management algorithms that we do in SAP IQ were linear, and they did not scale to the number of files that we needed to use. So clearly, this approach had its limitations and wasn't what we were looking at. To put things into perspective, other RDBMS systems such as Snowflake's partitions the data horizontally and stores data of these partitions on the object stores. So the files that we are moving here were much larger than the units that are used by Snowflake's, a system like a Snowflake. So we went back to the drawing board and we started to think of a different approach. So we started to look at how does data flow between the query engine and the shared block storage. So at the load and the query engine layer, it deals with database objects, which are pages. And in the shared block storage layer, it deals with files and blocks. Data is read from the shared block storage by the storage manager. The storage manager needs to translate those blocks into objects and then pass them on to the load and query engine. And this was done with the help of heavyweight data structures such as the free list. This free list and other data structures similar to it are not scalable, even if the underlying shared storage system can elastically scale. So with cloud object stores, many of these operations can be simplified. And the idea is that we want to directly map database objects into cloud objects. So we got rid of the shared block storage device, and we replaced it with an object store. Database objects or pages are passed from the query engine to the storage manager, and the storage manager stores those directly on the object store as cloud objects. These database objects are 512 kilobytes in size, and are stored in compressed form on the object stores. And by doing this, we've eliminated many of the bookkeeping operations that were done at the free list level or at the free space management level. So this is the approach that we discuss in the paper, and we found that with this approach, it fit more naturally with how the query engine processed units of data, but this didn't address other issues such as latency. And for that, we implemented a caching layer we call the Object Cache Manager that uses SSD devices that are attached to EC2 instances to store the data or to cache data. This, coupled with the prefetching gear that I've discussed earlier, we were able to address many of these latency issues. In the paper, we talk about other topics such as the management of pages in the buffer pool, the object key generation, the recovery and garbage collection, object cache manager, and snapshots. And we're not going to discuss them here in this presentation. They're all discussed in detail in the paper. So with this approach, we were able to make targeted changes to IQ to allow it to use object stores as native storage devices. What this meant is that we preserved IQ's existing feature set. We made no changes to IQ's load and query engine, but we were able to achieve lower cost and better performance by using object stores. And on that note, I pass in the presentation to my colleague, Xi, to talk about the performance evaluation.
Thanks, Mohammed. So for the performance evaluation, we have done 3 sets of experiments. The first is comparing the load and query performance between our native storage approach on S3 and other shared block storage, such as EFS. In the following slides, we will show that competitive performance is achieved by providing high throughput and low latency. We also compare the monetary cost and show that significant savings is achieved by dumping SAP IQ to the cloud. We evaluate the scale-up feature by increasing the compute power of one single node, and the scale-out feature is evaluated by increasing the number of nodes in a multiplex setup. In the first experiment, we use a single EC2 instance to load TPCH 1000 dataset. The EC2 instance we use is fairly powerful with 96 CPUs. After loading the data, the benchmark queries are run sequentially. And we repeat the same experiment on EFS. The first result we show here is a comparison of load time. In this graph and the graphs we are going to show in the following slides, the blue bar represents S3 using our cloud-native storage, and an orange bar is EFS using block storage. And we can see here that it takes much less time to load the test data using our approach. The load time is almost 6 times faster. Continuing with our next graph is the time to run the TPCH bench queries. The time shown here is in log scale. Again, we can see that in most cases, the queries run an order of magnitude faster on S3 using our approach. The reason is twofold. First, our approach is able to use the almost unlimited throughput on S3 because of parallel I/O and prefetching techniques as mentioned by Mohammed. And secondly, we are able to hide the high latency of S3 thanks to the Object Cache Manager, the OCM. There are, however, 2 exceptions, Query 2 and Query 19. We find that they are short-running queries. One takes less than 10 seconds, and the other takes less than 1 second. So in those cases, parallelism and prefetching are not enough to mask the latency of S3. In a follow-up experiment, we study the monetary cost of each approach. The cost is calculated by using pricing publicly advised by Amazon. The graph shows here is the cost to store the data at rest. The TP-CH1000 dataset has 1 terabyte of data, and it is compressed to around 520 gigabyte in IQ. We can see here that the monetary cost of storing that data is about $12 monthly on S3 using our approach. And it's significantly cheaper than EFS, which is around $160. The next graph we see is the cost to load and query the data. We can see the query cost in our approach is again cheaper than EFS. And for loading the data, the costs are close, but it's still slightly cheaper on S3 using our approach than using block storage on EFS. We also run the load and query experiments without OCM and compare the results. We find with OCM, there is a 25% improvement in execution time because OCM masks the high latency of S3 by providing caching on faster storage, such as SSDs. As for the compute cost, OCM also plays an important role because it reduces the number of S3 GET requests. From the result, we find that it brings about 32% savings in cost. And next, let's talk about the scale-up experiment. In this experiment, we again load TP-CH1000 dataset into S3 and run the benchmark queries. The same experiment is repeated on instances with increasingly larger compute power. As shown in the graph, we observe almost linear scalability. As the number of CPUs increases, the execution time decreases. The performance gains from 48 to 96 CPUs are slightly less than from 16 to 48 CPUs. We have done some further inspection and find the reason is that the network bandwidth is saturated at some point during this experiment. So in order to achieve better scalability, we have to scale out. And this brings us to our next experiment. In the scale out experiment, we construct 8 query streams that are pseudo-random permutations of TP-CH1000. These query streams are run in parallel on a multiplex of 2, 4, and 8 secondary nodes. We can see that the system scales very nicely. When the number of nodes is doubled, it takes almost half of the time to run the queries. The reason behind this linear scalability is that we are able to increase the throughput on S3 when more nodes are added to the setup. For block storage devices such as EFS and NetApp, the throughput is restricted either by the data size or the provision size, so they cannot scale elastically as in our approach. And with that, we have concluded the performance evaluation part of our presentation. And back to you, Mohammed.
Thank you, Shi, for these excellent results. And now we'll wrap up with a summary of the accomplishments of this work and what was discussed in the paper. We have made targeted changes to IQ in order to preserve its rich feature set. We stored query engine data units, which are pages, directly on object stores instead of block devices. And by using object stores, we were able to unlock many of the features that they provide, and we can reduce our storage cost while improving the query and load performance of our system. And with that, we reached the end of the presentation. So thank you for listening.